And now in this lecture we'll find out the area of the green shape. In the drawing we have a quarter circle, AOB is a quarter circle, and we have also tangent QP. This is tangent QP, that is tangent to the quarter circle here at this point. We know that this angle BQP, it is a right angle, it is equal to 90 degrees in its size. This is angle APQ, that is also a right angle, it is equal to 90 degrees in its size. In addition, we know that side BQ equals to 3 units in its length, side AP equals to 6 units in its length. And again, our mission is to find out the area of this green shape. So first of all, we define the point of tendency of tangent QP with this quarter circle, this point as point S. In the next step, we join points O and S together by a straight line. So what is the definition of line segment OS? Point O is the center of the quarter circle, point S is the point on the quarter circle itself, therefore OS is the radius of this quarter circle. We define the radius of the quarter circle as x, so x is the radius of the quarter circle, therefore OS equals to x, this is the radius of the quarter circle. In the next step, we'll do construction, that is to say, from point B, we'll go perpendicular on OS. Again, from point B, we'll go perpendicular on OS. So, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and OS as M. Here we have the radius OS that is equal to x. The radius OS is known to point S, that is the point of tendency of tangent QP with this quarter circle. Whenever you have a radius that is known to the point of tendency, then tangent QP will be perpendicular to the radius Q, or to the radius SO. If QP is perpendicular to SO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. So inside this small quadrilateral BMQS, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing fourth angle here must be equal to 90 degrees in its size. So inside the small quadrilateral BMQS, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral BMQS as a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle BMQS, side BQ must be equal to the opposite side MS. But BQ equals to 3, therefore MS must be also equal to 3 units in its length. And we also know that the opposite sides of a rectangle are parallel to each other. So in rectangle BMQS, side BQ must be parallel to side MS. So I write it down. BQ is parallel to MS in rectangle BMQS. Rectangle BQMS. This line segment MS or side MS is part of OS. And OS is the radius of this quarter circle, therefore it is absolutely a straight line. So OS is a straight line, so part of the straight line OS, that is MS, is parallel to BQ. So if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. So MS is parallel to BQ, therefore the straight line OS must be also parallel to BQ. So I write it down, OS must be also parallel to BQ. So we know that OS is parallel to BQ. So in quadrilateral BOSQ, we have side OS that is parallel to the opposite side BQ. So in quadrilateral BOSQ, we have one pair of parallel sides, therefore quadrilateral OSBQ is a trapezoid. So I write it down. Quadrilateral BS OQ is a trapezoid. This quadrilateral BOSQ is a trapezoid. Actually, the definition of a trapezoid is a quadrilateral with one pair of parallel sides. Okay, therefore quadrilateral BOSQ is a trapezoid. Okay. So what is the length of this line 7 OM? From the drawing it is very easy to see that OM equals to OS minus MS. Again, OM equals to OS minus MS. So I write it down. OM equals to OS minus MS. So OM equals to OS, that is X, it is the radius of the quarter circle, minus MS, that is 3. So in total, OM equals to X minus 3 units in its length. OM equals to X minus 3 units in its length. In the next step, we'll do another construction, that is to say, from point A, we'll go perpendicular on OS. Again, from point A, we'll go perpendicular on OS. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and OS as N. So in quadrilateral NASP, inside this quadrilateral NASP, we have 1, 2, 3 rectangles, therefore the fourth missing angle must be equal to 90 degrees. So actually, in quadrilateral NASP, we have 4 rectangles, therefore any quadrilateral that has 4 rectangles must be at least a rectangle if not a square. So we relate to this quadrilateral NASP is a rectangle, and we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NASP, side AP must be equal to side the opposite side NS. AP equals to NS, but AP is 6, therefore NS must be also equal to 6 units in its length. So write it down. NS is equals to 6 units in its length. And we also know that the opposite sides of a rectangle are parallel to each other. That is to say, side AP is parallel to the opposite side NS in rectangle NASP. So AP is parallel to NS. In rectangle ANSP. But SN is part of the straight line OS. Again, SN is part of the straight line OS. And we know that if part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. And because of the fact that NS is parallel to AP, it means that the straight line OS must be also parallel to AP. The straight line OS must be also parallel to AP. So actually we found out that in quadrilateral OAPS, in this quadrilateral we have one pair of parallel sides. That is to say, side OS is parallel to side AP, therefore this quadrilateral OASP is a trapezoid. So I write it down. Quadrilateral OASP is a trapezoid. Why? Because it has one pair of parallel sides. So actually we found out that quadrilateral OBQS is a trapezoid, and also quadrilateral OSPA is also a trapezoid. So what is the length of line segment ON or side ON? What is the length of side ON? ON equals to OS minus NS. Again, ON equals to OS minus NS. So ON is equals to OS minus NS. So ON equals to OS, that is the radius of the quarter circle, that is X, minus NS. We already found out that NS equals to 6. So NS is 6, so in conclusion found out that ON equals to X minus 6 units in its length. So this side of line segment ON is equals to x minus 6 units in its length. The next step will focus on this right triangle OAN, and we define this angle AON as alpha. So this angle equals to alpha according to our definition. So in the right triangle OAN, this angle equals to alpha, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus alpha. This is according to the rule that the sum of the angles in any triangle is equals to 180 degrees. So the missing angle equals to 90 degrees minus alpha. So we define 90 degrees minus alpha is beta, and therefore this missing angle equals to beta. If 90 degrees minus alpha equals to beta, it means that 90 degrees minus beta equals to alpha. Angle AOB, this angle AOB is a right angle, it is equals to 90 degrees. So 90 degrees minus this angle that is alpha must be equal to the missing angle here. Again, 90 degrees, that is angle AOB, minus this angle alpha equals to this missing angle. So 90 degrees minus alpha equals to this missing angle, and 90 degrees minus alpha is beta. So the missing angle here equals to beta. So in the right triangle OBM, this angle equals to beta, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus beta, and we already found out that 90 degrees minus beta equals to alpha, therefore the missing angle must be equal to alpha. So in the next step, we'll prove that those two right triangles can go into each other. Okay, but first of all, what is the definition of line segment OA? Point O is the center of the quarter circle. Point A is the point of the quarter circle itself. Therefore, OA is the radius of this quarter circle, that is equal to x, according to our definition. Likewise, what is the definition of line segment OB? Line segment OB starts from point O, that is the center of the quarter circle, and ends at point B, that is the point of the quarter circle itself. This is exactly the definition of a radius. So OB is also the radius of this quarter circle, that is equal to x according to our definition. So in the next step, we'll prove that those two right triangles can go into each other. That is to say, the right triangle OAN is congruent to the right triangle OMB. So write it down. We'll prove that the right triangle OAN OAN is congruent to the right triangle OMB. So why those two right triangles can go into each other? First of all, those two angles they are both equal to 90 degrees, therefore they are equal to each other. So this is angle ONA. and it is equal to this angle, that is angle OMB. Repeat again, angle ONA in the right triangle, OAN is equal to angle OMB in the right triangle OMB. They are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles, they are both equal to alpha, therefore they are equal to each other. So this is angle AON, and is equal to this angle, angle OBM. Repeat again, angle AON in the right triangle OAN equals to angle OBM in the right triangle OMB. They are both equal to alpha, therefore they are equal to each other. And those two angles, they are both equal to beta, therefore they are equal to each other. So this is angle OAN, and it is equal to this angle, it is actually angle BON. Repeat again, angle OAN in the right triangle OAN equals to angle BOM in the right triangle OMB. They are both equal to beta, therefore they are equal to each other. And finally, those two sides, they are both the radii of the circle is equal to x, therefore they are equal to each other. So this is side OA in the right triangle AON, and it is equal to this side, side OB, in the right triangle OMB. Repeat again, side OA in the right triangle OAN equals to side OB in the right triangle OMB. They are both equal to x. They are both the radii of the circle that is equal to x, therefore they are equal to each other. We actually proved that those two right triangles can go into each other according to angle side, angle rule. So I write it down. Right triangle OAN is congruent. This is the sign of congruent to the right triangle OMB. According to angle side angle rule. So what is angle side angle rule? Actually, if you prove the two angles and the side that included between those two angles of one triangle are correspondingly equal to two angles and the side that included between those two angles in a second triangle, then you actually proved that the two right triangles can go into each other according to angle side angle rule. And we proved that those two angles, alpha and beta, and the side between those two angles, that is OA in the right triangle AON are corresponding equal to those two angles that are alpha and beta, and the side that included between those two angles, this is OB in the right triangle OMB. Therefore, we prove that those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that side ON in the right triangle AON is equals to side MB or side BM of the right triangle OMB. Because again, from the fact that the two right triangles can go into each other, we will derive that side ON in the right triangle AON equals to side BM in the right triangle OBM, according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides ON and BM must be also equal to each other. And we have already found out that ON equals to x minus 6. Here ON equals to x minus 6, so we can write here that ON equals to x minus 6 units in its length. And from this equation, x minus 6 equals to ON equals to BM. We will derive that BM is also equals to x minus 6. BM equals to x minus 6. Here, this side BM equals to x minus 6 units in its length. So, we can also derive from the fact that those two right triangles can go into each other that side AN of the right triangle AON is equals to side OM of the right triangle OMB. And again, we conclude that AN, side AN in the right triangle AON equals to side OM in the right triangle OMB, according to the sum rule. But we have already found out that OM equals to x minus 3. Here, OM equals to x minus 3. So we can write here that OM equals to x minus 3. And from this equation, AN equals to OM equals to x minus 3. We will derive that AN is also equals to x minus 3. So this side AN equals to x minus 3 units in its length. In the next step, I will copy the right triangle ONA in a new page and we'll implement on this right triangle ONA the Pythagoras theorem. We just right now found out that side AN equals to x minus 3, and we already found out that side ON equals to x minus 6. And the hypotenuse OA of the right triangle OAN equals to x units in its length. This is the radius of the quarter circle. So actually, this is the right triangle OAN that I copied from the original drawing. Here, by PT is the formation for Pythagoras theorem, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle OAN, the hypotenuse is OA, therefore the square of the hypotenuse is OA squared, and it must be equal to ON squared plus NA squared. So here OA is x, therefore OA squared is x squared, and it is equal to ON squared. ON is x minus 6, therefore ON squared is x minus 6 squared plus NA squared. NA is x minus 3, therefore NA squared is x minus 3 squared. So in conclusion, found out that x squared equals to x minus 6 squared plus x minus 3 squared. We will open the brackets on this side of this equation, and we get that x squared equals to x minus 6 squared. X minus 6 squared is x squared plus 6 squared, that is 36, minus 2 times x times 6 is minus 12x, plus x minus 3 squared. X minus 3 squared equals to x squared plus 3 squared, that is 9, minus 2 times x times 3 is minus 6x. So here we have x squared on both sides of the equation, so x squared will get cancelled. After cancelled x squared on both sides of the equation. In this side of the equation we left of nothing, so it is 0. That equals to, here we have 36 plus 9 is 45, plus x squared minus 12x minus 6x is minus 18x. So in conclusion, found out that x squared minus 18x plus 45 equals to 0. And again, we found out that x squared minus 18x plus 45 equals to 0. So this is a quadratic equation. And the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 4a. In our specific quadratic equation, x squared minus 18x plus 45 equals to 0. The coefficient a equals to 1, the coefficient b equals to minus 18, and the coefficient c equals to 45. Now we put the data inside this general formula in order to find out the value of x. And we get that x equals to minus b. b is minus 18, therefore minus b is minus 18, that is 18, plus minus square root of b squared. b is minus 18, so b squared is minus 18 squared, that is 324, minus 4 times a is 1, so minus 4 times 1 is minus 4, times c, that is 45, so minus 4 times 45 is 180, divided by 2a. A is 2, so 2 times a is 1, so 2 times 1 is 2. So if we found out that x equals to 18 plus minus square root 324 minus 180 is 144 divided by 2. So x equals to 18 plus minus the square root of 144 is 12 over 2. So here we will have two solutions that are possible for x. The first solution for x is that x equals to 18 plus 12 over 2. 18 plus 12 is 30, and 30 over 2 is 15. So the first solution for x is x1 equals to 15. And the second solution for x is that x equals to 18 minus 12 over 2. 18 minus 12 is 6, and 6 over 2 is 3. So if we found out that x2 equals to 3. According to the second solution, x equals to 3. But we have already found out that this is side BM that equals to x minus 6. So BM is equals to x minus 6 units. BM is a length, therefore as a length it must be a positive number. So I write this down, BM is a length, and as a length it must be a positive number. That is to say, x minus 6, that is the length of line 7BM, must be a positive. That is to say, it must be greater than 0. If x minus 6 is greater than 0, it means that x is greater than 6. If we already found out that x must be greater than 6. If x must be greater than 6, x cannot be equal to 3. So we cancel this solution, because 3 is less than 6. Therefore, we left only with the with the first solution that is possible for x. That is to say, x equals to 15 units in its length. So here x equals to 15, that is to say OB is equal to x equals to 15 units in its length. OA is equal to x is also equals to 15 units in its length. OS is equal to x, also equals to 15 units in its length. Here NA is x minus 3, x is 15, so 15 minus 3 is 12, so we've already found out that NA equals to 12 units in its length. SP must be also equal to 12 units in its length. And here QS equals to BM, and BM equals to x minus 6, x is 15, so 15 minus 6 is 9, so QS equals to 9. So what is the area of trapezoid? The area of any trapezoid This is trapezoid ABCD. In this trapezoid ABCD, side AC is parallel to the opposite side BD. That is the reason this quadrangle ABCD is a trapezoid. So what is the area of this trapezoid? The area of trapezoid ABCD so the area of trapezoid ABCD equals to AC plus BD. It is the sum of its parallel sides. The parallel sides AC and BD are defined as the bases of these trapezoids. So it is the sum of its bases AC plus DC times the height. The height is DC, so we define the height DC as H. Over 2. Okay, so the area of any trapezoid equals to the sum of its bases times the height over 2. So what is the area of the green shape? The area of the green shape is equals to the area of this shape in total, and this shape consists of two trapezoids. It is trapezoid OBQS plus the area of the second trapezoid OSPA. So the area of the green shape equals to the sum of the areas of those two trapezoids. That will give us the area of this shape in total. Again, the area of the green shape equals to the sum of the areas of those two trapezoids. That will give us the area of the shape in total minus the area of the quarter circle OAB. So it is minus the area of the quarter circle. So repeat again. The area of the green shape equals to the area of this shape in total minus the area, and the area of the this shape in total equals to the area of trapezoid OSQB plus the area of trapezoid OAPS minus the area of this quarter circle OAB. So the area of the shape in total is the sum of the areas of the two trapezoids minus the area of the quarter circle will give us exactly the area of this green shape. So what is the area of trapezoid OBQS? This trapezoid OBQS. The area of trapezoid OBQS equals to the sum of its bases. That is to say, it is BQ plus OS times the height, that is QS, over 2. So the area of trapezoid OBQS equals to BQ plus OS times QS over 2 plus the area of trapezoid OSPA. What is the area of this trapezoid OSPA? The area of trapezoid OSPA equals to the sum of its bases, that is to say it is OS plus AP times the height, that is SP, over 2. Repeat again, the area of trapezoid OSPA equals to OS plus AP, that is the sum of its bases, times the height, that is SP, over 2, minus the area of this quarter circle OAB. What is the area of the quarter circle OAB? The area of any quarter circle equals to the area of the circle over 4. And the area of the circle of radius x is pi x squared. So it is pi x squared over 4. X equals to 15. So what is the area of trapezoid OBQS? Is equals to BQ, that is 3, plus OS, it is the radius of the quarter circle, that is 15, so this OS is 15, times the height, that is QS. QS is 9 divided by 2. In proportion followed, the area of trapezoid OBQS equals to 3 plus 15 times 9 over 2 plus the area of trapezoid OSPA. What is the area of this trapezoid OSPA? The area of trapezoid OSPA equals to OS, that is 15, plus AP, that is 6, times the height SP, that is 12, over 2. Repeat again, the area of trapezoid OSPA equals to 15 plus 6 times 12 over 2, minus the area of the quarter circle OAB is equals to pi x squared over 4. X is 15, therefore x squared is 15 squared, that is 225. So this expression in total, pi x squared over 4, is equals to 225 pi over 4. So the area of the green shape in total equals to 3 plus 15 is 18, and 18 over 2 is 9, and 9 times 9 is 81. So the area of trapezoid OBQS equals to 81 square units, plus the area of trapezoid OSPA is equals to 15 plus 6 is 21, times 12 over 2 is 6, and 21 times 6 is 126. So in total, the area of trapezoid OSPA is 126 square units, minus the area of the quarter circle. The area of the quarter circle in total equals to 225 pi over 4 square units. So this expression in total is equals to 176.714 square units. That is to say, the area of the quarter circle in total is equals to 136.714 square units, and 81 plus 126 is 207. So 207 square units. This is the area of this shape in total, minus the area of the quarter circle, that is 176.714 square units. So 207 minus 176.714 is equals to 30.285 square units. So in conclusion, found out actually the area of the green shape in total is equals to 30.285 30.285 square units. Repeat again. The area of this green shape is equals to 30.285 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. So in the drawing, we have a quarter circle. A or B is a quarter circle, and we also have, this is tangent QP, that is tangent to this quarter circle here is this point. And we also have here in the drawing angle BQP, that is a right angle. Angle APQ is also a right angle. Side BQ equals to 3 units in strength. Side AP equals to 6 units in strength. Again, our mission is to find out the area of this green shape. So in the first step, we actually going points O and S together by straight line. What is the definition of line segment OS? Line segment OS starts from point O, that is the center of this quarter circle, and that's at point S, that is the point of the quarter circle itself. This is exactly the definition of a radius. So OS is the radius of this quarter circle, that is equal to X. So here X is the radius of the quarter circle according to our definition. Actually, in the next step, we did a construction, that is to say from point B, we do perpendicular on OS. Again, from point B, we do perpendicular on OS. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point B and OS as M. And we also can implement here rule 1. According to rule 1, whenever you have a radius that is drawn to the point of tendency, here the radius OS is drawn to point S, that is the point of tendency of tangent QP with this quarter circle, and whenever you have a radius that is drawn to the point of tendency, then tangent QP will be perpendicular to the radius SO. If QP is perpendicular to SO, it means that this angle equals to 90 degrees and this angle equals to 90 degrees according to rule 1. So inside this quadrilateral BMQS, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees plus the size of the fourth angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, the missing angle here must be equal to 90 degrees in its size. So inside quadrilateral BMSQ, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral BMSQ as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle BMQS, side BQ must be equal to the opposite side MS. But BQ equals to 3, therefore MS must be also equal to 3. We also know that the opposite sides of a rectangle are parallel to each other. So side BQ must be parallel to side MS in rectangle BMQS. Repeat again, side BQ must be parallel to side MS in rectangle BQMS. So BQ is parallel to MS. OS is the radius of the quarter circle, therefore it is absolutely a straight line. So OS is a straight line and MS is part of OS, that is a straight line. So MS that is part of the straight line OS is parallel to BQ. If a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Therefore, the straight line OS must be also parallel to BQ. Here, the straight line OS must be also parallel to BQ. So in quadrilateral OSBQ, this quadrilateral OSBQ, side OS is parallel to side BQ, and therefore quadrilateral OSBQ is a trapezoid. Quadrilateral BSOQ is a trapezoid. Actually, the definition of a trapezoid is a quadrilateral with one pair of parallel sides. For that reason, a quadrilateral BOSQ is a trapezoid. And what is the length of side OM or line segment OM? From the drawing it is very easy to see that OM equals to OS minus MS. Again, OM equals to OS minus MS. It is very easy to see it from the drawing. So OM equals to OS, that is the radius of the quarter circle, that is X, according to our definition, minus MS, that is 3. So in total, OM equals to X minus 3. OM equals to X minus 3 in its length. In the next step, we did another construction. That is to say, from point A, we do perpendicular on OS. Again, from point A, we do perpendicular on OS. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and OS as N. So, inside quadrilateral OA, AN, SP, inside this quadrilateral we have 1, 2, 3 at angles. Therefore, the fourth angle must be also equal to 90 degrees. Therefore, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral AP and S with 4 right angles as a rectangle. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side AP equals to the opposite side NS. But AP is 6, therefore NS must be also equal to 6. So here NS equals to 6. And we also know that the opposite sides of a rectangle are parallel to each other. That is to say, in rectangle AN SP, side AN is parallel to side NS. Repeat again. In rectangle AN PS, side AP is parallel to the opposite side NS. So AP is parallel to NS. But NS is part of the straight line OS. Again, NS is part of the straight line OS. So if NS is parallel to AP, then the straight line OS must be also parallel to AP. So OS is also parallel to AP. So in quadrilateral OAPS, in this quadrilateral OAPS, side OS is parallel to side AP. Therefore, quadrilateral OAPS is a trapezoid. Quadrilateral OAPS is a trapezoid. What is the length of line segment ON? From the drawing it is very easy to see that ON is equals to OS minus NS. Again, ON equals to OS minus NS. ON equals to OS minus NS. So ON equals to OS, that is X, it is the radius of the quarter circle, that is equal to X according to our definition, minus NS. We already found out that and s equals to 6. So in total, ON equals to x minus 6 units in its length. ON equals to x minus 6 units in its length. In the next step, we focused on the right triangle ONA. In the right triangle ONA, we define this angle as alpha. So in the right triangle ONA, this angle equals to alpha, this angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus alpha, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So this angle equals to 90 degrees minus alpha. We defined 90 degrees minus alpha as beta. Therefore, the missing angle equals to beta. We know that angle AOB, the big angle AOB is the right angle, it is equal to 90 degrees because AOB is a quarter circle. So 90 degrees angle AOB is equal to 90 degrees plus this angle alpha must be equal to the missing angle here. Again, 90 degrees minus this angle alpha must be equal to the missing angle. So the missing angle here equals to 90 degrees minus alpha. And according to our definition, 90 degrees minus alpha equals to beta. So the missing angle here equals to beta. So in the right triangle OMB, this angle equals to beta. This angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus beta. But 90 degrees minus beta equals to alpha. So the missing angle here equals to alpha. In the next step, here actually, line segment OA is the radius of this quarter circle that is equal to x. Why? Because it starts from point O, that is the center of the quarter circle, and ends at point A, that is the point on the quarter circle itself. Therefore, OA is the radius of the quarter circle that is equal to x. Likewise, line segment OB, it is also the radius of the quarter circle that is equal to x units in its length. Why? Because line segment OB starts from point O, that is the center of the quarter circle, and ends at point B, that is the point on the quarter circle itself. This is exactly the definition of a radius. So OB is the radius of this quarter circle that is equal to x. In the next step, we proved that the right triangle ONA is congruent to the right triangle OMB. So why those two right triangles congruent to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to alpha, therefore they are equal to each other. And those two angles are both equal to beta, therefore they are equal to each other. So all the three angles in the right triangle O and A are correspondingly equal to all the three angles in the right triangle OBM. And also side OA in the right triangle ONA is equal to side OB in the right triangle OMB. They are both the radii of this circle that is equal to x, therefore they are equal to each other. So actually proved that those two right triangles can go to each other according to angle side angle rule. So what is angle side angle rule? If you prove the two angles, that the side that is included between the two angles in one triangle are correspondingly equal to two angles in the side that is included between the two angles in the second triangle, then you actually proved that the two triangles can go into each other according to angle side angle rule. And we proved that those two angles alpha and beta, and the side between them that is OA in the right triangle OAN are correspondingly equal to those two angles that are alpha and beta, and the side between those two angles that is OB in the right triangle OMB. Therefore, we proved that those two triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that side ON in the right triangle OAN is equal to side BM in the right triangle OBM. According to the rule that corresponding sides and congruent triangles are equal to each other. Those two right triangles can go into each other, therefore the two corresponding sides must be also equal to each other. Repeat again. ON equals to BM. But we have already found out that ON equals to x minus 6. Here ON equals to x minus 6. So we can write here that ON equals to x minus 6, and from this equation x minus 6 equals to ON equals to BM, we derive that BM is also equals to x minus 6. Here BM equals to x minus 6 units in its length. Again, from the fact that those two right triangles can go into each other, we can also conclude that side AN in the right triangle AON is equals to side OM in the right triangle OBM. Again, side AN equals to side OM. And again, side AN equals to side OM. But we have already found out that OM equals to x minus 3. Here, OM equals to x minus 3. So we can write here that OM equals to x minus 3. And from this equation, AN equals to OM equals to x minus 3. We will derive that AN is also equals to x minus 3. If this side AN equals to x minus 3 units in its length. In the next step, I copied the right triangle AON in a new page and implemented this right triangle AON, the Pythagoras theorem. This is the right triangle AON. Side ON equals to x minus 6, side AN equals to x minus 3, and the hypotenuse AO equals to x. It is the radius of the quarter circle. According to the Pythagoras theorem, in the right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. So in the right triangle AON, it means that AO square equals to ON square plus NA square. Again, AO square or OA square equals to ON square plus NA square. OA square equals to ON square plus AN square. OA is x, therefore OA square is x square. And it is equals to ON square. ON is x minus 6, therefore ON square is x minus 6 square plus AN square. AN is x minus 3, therefore AN square is x minus 3 square. So x square equals to, in conclusion, found out that x square equals to x minus 6 square plus x minus 3 square. So x square equals to x minus 6 square. X minus 6 square equals to x square plus 6 squared, plus 6 squared, that is 36, minus 2 times x times 6, that is minus 12x, plus x minus 3 square. X minus 3 square equals to x square, plus 3 squared, that is 9, minus 2 times x times 3, that is minus 6x. Here we have x square on both sides of the equation, so x square will get cancelled. After we cancel x square, here we left, in this side of the equation we left with nothing, so it is 0. That is equals to, here 36 plus 9 is 45, plus x squared, and minus 12x minus 6x is minus 18x. So in conclusion, found out that 0 equals to 45 plus x squared minus 18x. Repeat again, in conclusion, found out that 0 that x squared minus 18x plus 45 equals to 0. So this is a quadratic equation. Okay, again, this is a quadratic equation. And the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And when we find out the value of x, according to this special formula, x is equals to minus b plus minus 4 to b squared minus 4 times ac over 4a. In our specific quadratic equation, quadratic equation, the coefficient a equals to 1, the coefficient b equals to minus 18, and the coefficient c equals to 45. Now, we have to put the data inside this equation in order to find out the value of the values of x. X is the radius of the quarter circle. So according to this general formula, x equals to minus b. B is minus 18, so minus b is minus 18, that is plus 18, plus minus square root of b squared. B is minus 18, so b squared is minus 18 squared, that is 324, minus 4 times A times C. So it is minus 4 times A is 1, so minus 4 times 1 is minus 4, times C, that is 45. So minus 4 times 45 is minus 4 times 45 is minus 180 divided by 2A. A is 1, so 2A divided by 2A. So A is 1, so 2 times A, that is 1, 2 times 1 is 2. So we're going to find out that x is equals to 18 plus minus go to 324 minus 180 over 2. So x equals to 18 plus minus 324 minus 120 is 144, so inside the root we left only 144 divided by 2. So x equals to 18 plus minus, the square root of 144 is 12, so it is x equals to 18 plus minus 12 over 2. So here we have two solutions that are possible for x. The first solution for x is that x equals to 18 plus 12, that is 30 over 2. 30 over 2 is 15. So the first solution for x, x1 equals to 15, and the second solution for x is that x equals to 18 minus 12 over 2. 18 minus 12 is 6, and 6 over 2 is 3. So the second solution for x, x2 equals to 3. The second solution is an incorrect solution. Why the second solution is incorrect? Because we have already found out that the length of line 7bm is x minus 6. Again, bm equals to x minus 6. Line 7bm is a length, and as a length it must be a positive number. So the length of bm that is x minus 6 must be a positive number. That is to say it must be greater than 0. If x minus 6 is greater than 0, it means that x is greater than 6. So we actually found out that x must be greater than x. If x is greater than x, it is impossible that is equals to 3. So the solution that x equals to 3 is incorrect. We cancel this solution and we left with the only solution that is possible for x. That is to say x equals to 15 units in its length. Then I presented to you the formula for the area of a trapezoid. A trapezoid is a quadrilateral that has one pair of parallel lines. Here we have quadrilateral ABCD. In this quadrilateral ABCD, side AC is parallel to side BD. So what is the area of this trapezoid ABCD? The area of trapezoid ABCD equals to the sum of its bases. The bases are defined as the parallel sides, that is to say AC and BD. So it is AC plus BD, that is the sum of its bases, times the height, here, this is the height, over 2. Again, the area of a trapezoid equals to the sum of its bases. It is AC plus BD times the height, it is CD, the height transgress 90 degrees with the bases, over 2. Okay. So, what is the area of the green shape? The area of the green shape equals to the area of this shape in total minus the area of the quarter circle. Again, the area of this shape in total minus the area of this quarter circle AOB, it is equal to the area of the green shape. And the area of this shape in total, this shape in total consists of two trapezoids. The first one is trapezoid OBQS, and the second trapezoid is trapezoid OAPS. So the sum of the areas, so the area of the green shape equals to the sum of the areas of the two trapezoids, OBQS and OSPA. The sum of the areas of the two trapezoids will give us the area of this shape in total, and when we subtract from the area of this shape in total the area of this quarter circle, it will be equal to the area of the green shape. So the area of the green shape equals to the area of the shape in total, that is the sum of the areas of the two trapezoids, minus the area of the quarter circle AOB. So what is the area of trapezoid OBQS? The area of this trapezoid OBQS equals to the sum of its bases, that is OS plus BQ, times the height, that is QS, over 2. Repeat again, the area of trapezoid OBQS equals to the sum of its bases, that is BQ plus OS, times the height, that is QS, over 2. Plus the area of this trapezoid OSPA. What is the area of this trapezoid OSPA? The area of this trapezoid OSPA equals to the sum of its bases, that is AOS plus AP, times the height SP over 2. Repeat again, the area of this trapezoid OSPA equals to the sum of its bases, that is OS plus AP, times the height, that is SP over 2. So the sum of the areas of these two trapezoids is the total area of this shape, minus the area of this quadrilateral, of this minus the area of this quarter circle OBA. It is equals to the area of the green shape. So what is the area of this quarter circle OAB? The area of this quarter circle OBA equals to the area of the circle, that is pi x squared over 4, because x is the radius of the quarter circle. So the area of the quarter circle OAB equals to pi x squared, that is the area of the circle, divided by 4. Here BQ is 3, OS is 15, SQ is 9, divided by 2. Here OS is 15, AP is 6, SP is 12, divided by 2. Here we have pi x squared. X is 15, therefore x squared is 15 squared, that is 225. So in total, pi x squared over 4 is 225 pi over 4. Here 3 plus 15 is 18. 18 over 2 is 9, and 9 times 9 is 81. Here we have 15 plus 6 is 21, times 12 over 2 is 6. 21 times 6 is 126. This expression, 225 pi over 4, in total it is equal to 176.714. And 81 plus 126 is 207, and 207 minus 176.714, it is equal to 30.285 square units. So in conclusion, found out that the area of the green shape equals to 30.285 square units. I repeat again, the area of this green shape, it is equal to 30.285 square units. Okay, thank you very much.